Yeah, so let's start things off with if anyone has any questions about homework.
I have kind of a general question about GB6, and there's some homework that we could do.
Okay.
But it seems like there's a lot of ways to think about how to define GB6. Like, we've learned a lot of formulas. Like the first time we did the normal curvature times cosine some angle or something like that, and then we saw it as like the coefficient of the u cross t vector in the alpha double prime. It's
So
hard
G does
to
a curvature.
keep straight.
Yeah. Okay, so here's, just to summarize our discussion of curvature of curves, right? So it starts with the xy plane, and we can have some curve going around like this. We could call it, let's go ahead and parameterize it by length, right? Then in that case, beta prime of s is some unit vector, which we could write as, for example, cosine theta of s, comma sine theta of s. That's how we parameterize unit length vectors, right? And so then, and we learned a formula that there's we can define kappa to be theta prime of s. Okay. Now that's not the original definition we gave, but that's sort of the most intuitive notion of curvature, just in the two-dimensional plane. All right, it's the rate of change of direction, right? Does that make sense to everyone? Is that like it should be reasonably intuitive, right? This was something we calculated later. I mean, we computed this. I think you might have even had a homework problem where you computed this. Is that possibly the case? Yeah. Okay. And now, how is curvature defined more generally? Another way to do it is at any given point, right? The direction here is t is equal to beta prime of s, which is this, right? This would be t, right? And then you look at the rate of change of t, right? Okay, and so you can look at t prime of s. Now we know that t prime of s will always be perpendicular to t, right? Because t has constant length. Right, remember that's that standard trick, t dot t equals 1. And so therefore, take the derivative of that, and 2t times dot product t prime will equal 0. So these have to be perpendicular. This is, you can see it's turning to the left, right? And so you can only turn left or right. You can't turn forward or backwards, right? You can accelerate forwards or backwards, but we're saying it's a unit speed curve. And so the length of this t prime of s is kappa up to a sine. And so the convention was that kappa is positive if it's curving to the left, and it's negative if it's curving to the right. And under this definition, then exercise showed that kappa equals theta prime of s. Okay. Now notice that this kappa here is signed. It can be positive or negative. Okay. So that's maybe our first notion of curvature. Okay. Then our second notion of curvature came from the Frenet formulas. And this was more of a sort of a three-dimensional thing, but I think it's in the order that we learn things, so let me mention it. We have these Frenet formulas where at every given, this would be for curves in 3 dimensions, right? So we have some curves in 3 dimensions. And then the first vector was t as the direction of the curve. The second direction was n. You define, t. Let's go ahead again and take a unit speed curve. N was in the direction of beta double prime of s. And so what we do then is say that beta double prime of s is the same direction as n, and whatever that magnitude is, we call that kappa. And so by this formula, you could just say that this kappa here was just the length of beta double prime of s. And then we defined t to be t cross n, I think. Is that given in the right order? And then we had these Frenet formulas that the rate of change of these things with respect to s, okay, of s of s of s, it was also linear combinations of T, N, and B because they form an orthonormal frame. Was the whole point. And then this equaled kappa times, let's see here, T prime. This is T prime, right? Equals kappa times N. And then therefore by anti-symmetry, this is negative kappa T. And then we had somewhere B here. And was this plus torsion here?
Yeah.
Okay. And then, so whatever, the torsion was just defined wherever that coefficient was. And then by anti-symmetry, it means we have a minus torsion times N here. And I think these were the Frenet formulas. Am I right? T, N, and B? I think so. And so then we have this notion of curvature of a curve equaling the length of beta double prime of S. Okay, and then, but then we have this, the final notion that you really asked me about was geodesic curvature, right? And that is a slightly different thing. In fact, it's a similar symbol, it's kappa, but it has a G there for geodesic. So it's geodesic curvature. And this refers to the curvature of a curve in a surface. So we have some potato here, right? And then we have some curve on the surface of the potato. And the point is that geodesic curvature is just the curvature that's done on purpose, like the ant does on purpose. I mean, obviously, if the ant's trying to walk straight, they're still going to be curving three-dimensional space around the potato because the potato is curved, right? But you know, what curvature do you actually do on purpose? Then the geodesic curvature, you know, we can give it a definition. First of all, we need something to replace the Frenet formulas, and we need a local frame. So at any given point, again, we'll take this to be a unit speed curve. We have the tangent vector t, that's just beta prime of s. But then in terms of trying to get a local orthonormal frame, there's another vector, right, which actually is very natural, and that's the vector perpendicular to the surface at each point, right? Call it u, right? And this is true at every point. And so it's also right here coming out of the board, right? So it's hard for me to draw that, right? So imagine u coming out of the board, right? Perpendicular to the surface of the potato. And then what you can do is do u cross t, right? So u cross t by the right-hand rule is going to give me something like this, right? And by the way, this u has length 1. This t by definition has length 1 because we have a unit speed curve. And then therefore u cross t will have length 1. And so when we look at beta double prime of s, right, over here we just attributed all of the length of beta prime of s to the curvature. But here, when we look at beta double prime of s, first of all, it should be linear combinations of u, a t, u, and u cross t, right? So let's see here, it's going to be so many t, right, plus so many u plus so many u cross t. Is that fair? Mm-hmm. That forms an orthonormal frame. But then remember this trick we do over and over and over again, right? That, you know, beta prime of s dot product beta prime of s. Remember, we're assuming this is a unit speed curve, so that equals 1, right? And so we take the derivative of both sides, and we get 0 equals 2 beta prime of s dot product beta double prime of s. And this beta prime of s, that's t, right? So the component of beta double prime of s in the t direction is 0. This is a 0 right here. Okay. All right? And so, in other words, when you have a unit speed curve on the surface of a potato, there's curvature in the normal direction. We call that normal curvature. And there's the rest of the curvature. We call that geodesic curvature. And so this part here we'll call the geodesic curvature. And this we had a name for as well, right? Let's just call gave it a name. I think we called it was it k of beta prime of s? Normal curvature. I think, right? So it makes sense. We broke down. In other words, we break down the curvature vector. So beta prime of s is the curvature vector. Now we're breaking it down to two components, so that the geodesic curvature, in fact, is just beta double prime of s dot product u cross t. Okay, fair enough. And then this other term, the normal curvature, k of beta prime of s this, I guess, also is beta double prime of S dot product U, right? Which we also could relate to the shape operator. I'm sure this one I'm confident too. Is this correct, by the way, or am I off by a sign? Is this correct? Okay. Okay, yeah, so then what this also equals is, maybe someone helps me here, it's a beta prime of S dot product, the shape operator, whoops, I want to put parentheses there. The shape operator of beta prime of S. Now, why would that be? Easy exercise, right? You have to plug into the definition of what the shape operator is and exercise for it. Make sure you know how to do that. It's in the book. Okay, so there's some just general review of geodesic curvature. And so then we see that it's the curvature the ant on the potato chooses to do. It's the curvature to the left, it's the left-right component of the curvature. By the way, geodesic curvature can be positive or negative, which makes it more like this kind of curvature than this kind of curvature. This is curvature, the full three-dimensional curvature vector in 3 dimensions, right? This is, by the way, a definition of where you define geodesic curvature with a cosine theta or something, to me it's like, I don't think of it that way at all. Like, I don't like it. I mean, okay, it's fine, it's a theorem, right? But to me, that's not how I would choose to think of it. It's an exercise, I suppose, know the exercise, but it's just the curvature that the ant chooses to do. So, just basic examples, and if you have a round sphere, then the equator is an example of zero geodesic curvature. And more generally, by the way, this geodesic curvature is quite analogous to this curvature here. It could be positive or negative. And if it's positive, you're curving to the left, and if it's negative, you're curving to the right. You can think of it that way. Now we have to decide, well, what's left and what's right. You see here, there's a universal notion of, clockwise, counterclockwise. With any other tangent plane, like are you looking at it from this side or the other side? So there's that issue, right? And that ultimately comes down to things like your choice of U. And so ultimately, like when we have the Gauss-Bonnet formula, let's write that down. When you keep track of all the conventions, or theorem, let's say. This was sort of the highlight of the class in many ways, is you have some surface M, and then you have the boundary of M here, you notice is a circle. But by the way, the boundary of a two-dimensional surface is a one-dimensional thing, and a one-dimensional bounded thing has to be a circle. That's all the closed one-manifolds are just circles. And so then the Gauss-Bonnet formula says that the double integral over M of the Gauss curvature times the area form plus the integral over the boundary of M of the geodesic curvature ds, that this always equals 2 pi times the Euler characteristic of M. And in this convention, by the way, geodesic curvature, just to be clear, when you have a disk, right? The geodesic curvature, let's say it's a disk of radius r, geodesic curvature is 1 over r. But it's positive. So when you can think of it as when you're curving towards the surface, it's positive curvature. Now if you were curving, think of it as a disk, but where there's a place where it curves back on itself. So here you have the geodesic curvature would be positive over here, but between here and here, the geodesic curvature would be negative, okay? So if you go back to the proof, what you'll realize the conventions we're using is that when you're curving towards the surface, it's positive curvature, right? But when you're, see how the second derivative, it doesn't matter if you're going this way or that way, right? The second derivative, beta double prime of s, is pointing away from the surface, that's negative curvature. Okay, so here, positive curvature, negative curvature. And that follows from how we prove things. We just chase down all the conventions we were using at the time. And so in particular, if we take half of a disk, like this is the northern hemisphere, let's say, then you can see that the geodesic curvature of the equator, this is equal to 0, but the Gauss curvature of a sphere of radius r is 1 over r squared. And so in this case, notice that the double integral of k dA is equal to 2 pi, because it's only half a sphere. Normally the total area would be 4 pi r squared, but half a sphere is 2 pi r squared, and you multiply by 1 over r squared k. So this term here is 2 pi, and this term here is 0, right? The integral over the boundary of the geodesic curvature ds, that equals 0. And I like to compare that to the disk case here. And in the disk case, you see that the geodesic curvature integral over the boundary of m then of the geodesic curvature times ds. That's going to be 2 pi r, is the circumference, right? Times 1 over r gives me 2 pi again. And this is in a flat plane, so the double integral over m of k dA, that's just 0. And in both cases, notice that adds up to 2 pi total, which is good because the Euler characteristic of a disk, right, is 1. And so those are two examples of the Gauss-Bonnet theorem in action. Yes?
Is that K, like Gauss curvature, kappa? And if not, like what?
Whoa, which K are you talking?
KDA.
No, that's Gauss curvature.
Gauss curvature. So
No,
it's
it's got
kappa.
nothing to do with, this capital K here has units 1 over distance squared. So Gauss curvature has units 1 over distance squared. Curvature has units of 1 over distance. 1 over distance, geodesic curvature, 1 over distance, right? I remember what Gauss curvature is that if you have, what is Gauss curvature, right? K, right? Remember it equals K1, K2, right? Where if you take your surface, take the unit normal, take a point P. Now, what is the point? What is the Gauss curvature at the point P? What you do is you look at, this is capital U, right? Then look at little u, right? Now, little u is a unit vector that's tangent, so it's a circle of possible little u's, right? They're tangent to this surface. Think of it going around in a circle right here, right? Tangent to the circle, to the potato. And no, so for each little u, you might even call this u of theta, right? Because theta, kind of arbitrary, right? But it's a circle of them, right? And so each cross section, you get a cross-sectional curvature. Like if I take that u as drawn, you get this cross section. It's the intersection of the plane defined by capital U and little u and the surface, right? Going through P. And then you look at this cross-sectional curvature here, and it's also known as normal curvature. In fact, it's this whole thing, it's this thing here, right? Take the shape operator in that direction, dot product beta double prime of s, but it also equals this. I think, remember, K1 and K2 are the max and min of this normal curvature. Or cross-sectional curvature. Right, so for each direction here, u, I can plug it in here, right? So I can look at, so this is explicit, K1 and K2 equal the max and min of the cross-sectional curvature, which is also equal to just u of theta dot product the shape operator at P of u. So that u is a unit vector. It's a circle. Whatever the min is, call it K1. Whatever the max is, call it K2. The product, that's what Gauss curvature is. Yeah.
I know that the geodesic curvature around the equator of the sphere should be 0 because it's always, like, the direction of the u is always pointing outwards at that point. But now I'm confused because you drew above a disk where there's a geodesic curvature of 1 over r, and is the equator not just also a disk?
Oh, it's not. There's no reason. There's no right to call that an equator because it's a flat disk, right? If I have a flat piece of paper and I draw a circle, right? That's just a circle. So it'd be just like if I make this circle right here, I'm curving to the left quite clearly, right, to make that circle, right? Now, if I walk around the equator of the Earth, I think I'm walking straight the whole time. And if I don't know the world's round, I didn't even realize I made a circle.
So this is kind of like a circle in a two-dimensional plane, perhaps?
Yeah, actually, no, this is exactly that. The picture I'm trying to draw here, this is a plane. And then we just, like a flat piece of paper, draw a circle radius r. cut it out, right? So this is just a flat disk. So that's why the Gauss curvature is 0 at every point, but the geodesic curvature is 1 over r. And then just connect back to this notion here where the curvature in the plane, this two-dimensional curvature is just theta prime of s. That is what geodesic curvature is too. Geodesic curvature is theta prime of s as perceived by the ant. The ant is, when you're walking around the equator, you don't think you're turning at all. So theta prime of s is 0, right? So intuitively, it's what do you think your rate of change of turning is, right? And so, and then what's the formula for it? It's this thing right here. So that's actually how you compute it, right? So it's, look at your, parameterize your path by arc length, so that beta prime of s equals 1, right? And then just look at beta double prime of s, that's your curvature vector. And the component that's perpendicular to the surface you're on, you're unaware of, because you have no choice but to follow this, to stay on the surface. But the part that's to your left or right, that's your choice. I could turn left, I could turn right. So the component that points to the left, that is, just take dot product of u cross t, and that's geodesic curvature. Does that make sense? Other questions about geodesic curvature? Yes.
This is not geodesic curvature, but could we go over the different surfaces, like the S2 and the T2 and like
Oh,
their
yeah,
curvatures and
absolutely.
stuff?
Thank you for reminding me. And yeah, I was just planning to do that, in fact. So other questions about this? We'll move on. We'll erase this stuff here, for example. Because, we did the Gauss-Bonnet formula. And, but I think there are, if you look at the practice exams, there are some questions that actually try to use the Gauss-Bonnet formula to prove some interesting things. And so we didn't really talk about Euler characteristic that much, actually. So let's round out that conversation. I mean, what is the Euler characteristic of a surface? If you, let me give you, let's just start with a list of examples, okay? And then we'll figure it out. Suppose you have a sphere. What's the Euler characteristic? The Euler characteristic of that is 2. And this is a topological statement. It doesn't have to be a round sphere. It could be, just think of a beach ball that's deflated and you twist it however you want, right? Maybe it's even a little stretchy, right? As long as it's topologically a sphere, then it's topological quantity. The Euler characteristic is 2. What about the surface of a donut? Euler characteristic, no, it's not. It's 0. Just testing you there. And what about a donut with 2 holes, which I don't know why they don't sell these. I don't eat junk food, actually. You guys know I don't eat donuts at all. I haven't had a donut in nearly a year. And by the way, it's like, I can think clearly first time in my life. I encourage you to avoid stuff that's bad for you. As you get older, you become more sensitive to it, okay? That's -2. And does anyone want to guess what a 3-hole donut? But I think it would be a good marketing thing. I don't know why they don't sell these 2-hole and 3-hole donuts. Maybe they do.
They
something.
do 2 holes.
They do. Okay.
I like Wawa, I think.
I mean, because if you've never had one, you're gonna have to see if it tastes any different, right?
That's true.
Kind of like it's just for scientific reasons, right?
Isn't it? Actually, you're just getting less donut when there's more holes.
Maybe,
So,
I don't know.
It's probably
Okay, does
worse.
anyone want to guess what the other characteristic of this is?
-4.
Yeah, why not, right? It seems to be a pattern here, right? And then, and so on, right? You can see the pattern. Okay, and then there's another list of examples. By the way, I'm only going to show you, I'm starting off with examples that don't have boundary. Like this obviously has a boundary. And let me tell you, what's the Euler characteristic of this? By the way, when you have a hole like that, if I were to fill it in, I would get a donut, right? And Euler characteristic is, I'll remind you, it's faces minus edges plus vertices. And if you don't want to know what that means, or if you forgot, I'll remind you. But, so when I add a face, I get the Euler characteristic of 0. So the Euler characteristic of this must be -1. Does that make sense to everyone?
So does that not count as an added edge, the boundary?
It does. It does. Like if you were to triangulate this, you'd have like a vertex here, and a vertex here. Let's say so. It's like a triangle there, and you could have when you do the triangulation, you would have and so on, right? It goes around the edge. Okay. Some sort of triangulation, and we'll get into this again in just a second. But so if you just simply remove that face, right, then you have a surface with boundary, or you could put the face back in, now you have a surface without boundary, right? So since we know that f minus e plus v, when I put in that, see, the question is, do I put that face in? A face is a two-dimensional, that's a face right there, right? But do I, and this is a face, and this is a face. And if I put all those faces in, but the point is, if I leave that face, if I put that face in, then the weather characteristic is 0, and since it's f minus e plus v, it must have been -1 before I added the extra face. Does that make sense? Okay, so we'll do some more examples. But first, let's look at the list of surfaces that don't have any boundaries. Another one that's, in fact, here's what's kind of cool. I just gave you the complete list of all surfaces in R3. That's all possible surfaces that don't have boundary, that are embeddable in R3. Isn't that amazing? It's just donuts and donut holes. I guess that's a donut hole, right? Anyway, it's a sphere. You can buy these. All right, so you have a sphere, surface of a donut, 2-hole donut, 3-hole donut. That's it. Otherwise, it's called a sphere. That's called the surface of genus 1. It's called the surface of genus 2, the surface of genus 3. Fair enough?
There's no like weird self-intersecting Klein bottles. Do we care about those?
Those are immersible. A Klein bottle, for example, is immersible in R3, but not embeddable. Embeddable means no intersections.
Oh, okay.
Yeah, so these are all the ones that you can do without intersection.
Okay.
But yes, there are the weird ones. Okay, so now, if you were to believe that only 3 dimensions exist and anything more than 3 dimensions is nonsense or something like that, then we could kind of stop here. Or if you were unfamiliar with the notion of an abstract surface, like, do we actually think of a surface in R3? As I said before, when you plan your trip to Europe, do you pull out a globe and look at and spin it and start looking? No, you look at 2-dimensional maps on your phone, right? And so really, you're thinking about the surface of the Earth abstractly. You don't need a 3-dimensional space to understand the surface of the Earth. And so taking that notion, right, the question then becomes, are there other surfaces but perhaps not embeddable in R3? And the answer is yes. And the easiest one to visualize would be the Klein bottle. So the Klein bottle is, by the way, it's analogous to the torus. So let's talk about the torus for a second. The torus, we just draw it like this, right? But a nice way to do the torus is you could take a square piece of paper, and then what you could do is take the piece of paper and then roll it up and get a cylinder, right? I could identify this side like that. So let's just use that notation, and then you roll it up. And you identify those two sides like this. You guys see what I did? I rolled up the piece of paper and now I have a cylinder, right? And now the problem is the paper's not stretchy enough, so this is, but you can at least visualize it. Imagine we're made out of some rubber or something, right? Then you could just take it and stick it together like that, and I have the surface of a donut, right? And so over here, that's equivalent to, so we have these, we want to identify these sides here, okay? Like this, okay? And what this means is identify, this point gets identified with this point. In other words, the beginning part of this arrow, think of it as the beginning and the end. Just, so identify correspondingly, right? So these arrows matter, right? And so that gives you a torus. And this can be compared to a Klein bottle, which is where you take a square and you identify the first two sides like this. And you have a cylinder just as before. But now, instead of identifying this side with the other side, you switch it, right? So, and this still makes sense. So it turns out this point here, for example, gets identified with this point over here. Okay. Turns out that makes sense too. It's just that I can't embed it into 3 dimensions. I can immerse it into 3 dimensions. It looks like this. It's the famous Klein bottle. You take a bottle here, and then you take out a little hole out of the bottom and have it go this way. And then you have the neck come in like this. And now the problem is I want to connect them up, but the bottle itself is in the way. Do y'all see the problem? So what you do is you say, oh, no problem, this is embeddable in 4 dimensions, okay? In 4 dimensions, so this is XYZ space, everything is W value equal, so it's XYZ and W if I want to go to 4 dimensions, right? W is equal to 0 here everywhere. What I do is I simply go up to W equal to 1, I go over and in, right? And then lower W back down to 0, and then I connect up. So this is embeddable as a surface in R4. But in R3, we just draw it like this, and we have this self-intersection here, right? And just pretend like that didn't happen. Okay? And so that's your Klein bottle, which is what you get from this identification. And this is a surface without boundary, just not embeddable into 3 dimensions. Yes?
So for the torus, we know the Euler characteristic is 0.
Euler characteristic.
Euler, sorry.
Yeah.
We know it's 0, but with the faces minus edges plus vertices formula, how do we get that from like the drawing of the cylinder? Like, how do you identify a face versus an edge versus a vertex? That like, because if you just
Great question. Great question. So let's compute the Euler. By the way, I'm going to put the Euler characteristic of the Klein bottle is also 0, and I guess I can draw it right here. Right? Let's see here. Here's your Klein bottle, right? And that's called, by the way, well, we call it K2, right? By the way, we call this S2. We call this T2. We call this T2 connect some T2. We call this T2 connect some T2 connect some T2. And what does connect some mean? Connect some means exactly what you think it is. Take 2 donuts and sort of stick them together, right? So let me just do that first. Connect some. So it's like a plus sign, right? And then, so what does connect some mean? It means you take your 2 surfaces, you put them close to each other. You guys see what I'm doing there? And then you stick them together. Now, what does stick them together mean exactly? Well, you erase a neighborhood of a point here and erase the neighborhood of a point here, right? So I have a missing disk there and a missing disk there. And then you stick them together, right? So you literally just push them together. That would be fine. Or you can add a neck like that. Doesn't matter. And that gives you a new surface, which, and you can see in this case, is, oops. A 3-hole donut. And so that is how connect sum works. And by the way, you might say, well, does it matter where I erase the neighborhood of a point? No, because every point is kind of the same topologically, right? So pick any point here, pick any point there, it doesn't matter. You're going to get the same topological thing over here. We're not concerned about rigid structures, just how the overall connectivity of the object. And so it's interesting that all surfaces in R3, embeddable in R3, are connect sums, non-negative connect sums of tori. Or you think of it, take a sphere. I mean, in some sense, this is 0 connect sums of tori. You can, if I just define it that way, but and interestingly enough, by the way, connect sum with the sphere doesn't do anything. So you might say, hey, what's T2 connect sum in S? The answer is T2. Right, so we can actually draw the picture and see that, right? Take a donut, and then take a sphere, right? And now connect some of them, right? It's still a donut, right? Didn't change the topology at all. So connect something with the sphere doesn't change anything. So in some sense, that's in that sense, it's like so I can make the theorem that says if I take an n-hole donut, that has 0 holes, right? So a 3-hole donut plus a 7-hole donut equals a 10-hole donut. And I'll just define a sphere to be a 0-hole donut. Right? Okay. Now the question was about Euler characteristic. How do we? And you can see I'm making another list here of surfaces, right? And you can see the Klein bottle is the second one on the list over here. Second one, not the first one. So that kind of raises the question of what the first one is. Today what we do, I'm going to go ahead and make you wonder. You take an RP2, connect some RP2. That's what the Klein bottle is. It's actually something else connects some itself. And then, and by the way, this I won't even tell you what it is yet. I'll just tell you that this first thing here is an RP2. And it has weather characteristic 1. And when you connect it with itself, you get weather characteristic 0. And then if you do it 3 times, then you get weather characteristic -1. And if I do it 4 times, total of 4 times, then you get weather characteristic, anyone want to make a guess? -2. Yeah, it goes down 1 by 1 each time, right? And then so on, right? And also notice the pattern that this is exactly half that, right? So in some sense, these surfaces over here are kind of half of these surfaces over there. These surfaces here are in fact all the double covers of these surfaces. Right? Now we only know what one of them is, the Klein bottle. And so I'm telling you the double cover of the Klein bottle is a torus. So you're like, oh really? Okay, what does the word double cover mean? That's an interesting question. And what is an RP2? Okay, so I think we have 3 questions in that. What is RP2? What is a double cover? And also, what is weather characteristic? Okay. Let's start with weather characteristic. And my board work's not perfect here. Apologize. But let's start by computing the weather characteristic of some of the easier surfaces. Let's start with this sphere, right? So what is the weather characteristic of a sphere? Well, what you do is you triangulate it. So for example, this is the same thing as the weather characteristic of for example, a cube. So you just find some, what do you call it? Polyhedron that has the same topology. And so, more precisely, I need a bunch of faces, edges, and vertices so that it has the same connectivity as the surface in question. And this equals F minus E plus V, which in this case, how many faces are there for a cube? Well, there's 6 faces, right? A face is a two-dimensional thing. An edge is a one-dimensional thing, and a vertex is a zero-dimensional thing. Okay? So how many two-dimensional things are there? Well, there's 6 two-dimensional faces. How many one-dimensional edges are there? Well, there's the square on the bottom, the square on the top, that's 4 plus 4, and then you got the 4 vertical pieces, right? So 4 plus 4 plus 4, that's 12. How many vertices are there? Well, that's the zero-dimensional thing. These are the corners, right? 1, 2, 3, 4 on the top, 4 on the bottom. And notice that we get 14 minus 12, which is 2, right? But then you're like, wait a second, doesn't this depend on how we triangulate it? Like, what if we had done a tetrahedron, for example, right? Right? So a tetrahedron, its weather characteristic, right? That's also topologically a sphere, right? But how many faces are there? There are 4 sides to this tetrahedron, right? And then how many edges? Well, there's 6, right? And then how many vertices? There's 4, right? And that also equals 2, right? And so you're like, oh, I got 2 in both cases. And it turns out that's not a coincidence. It turns out however you triangulate your surface, you'll get exactly the same answer. Now, if you want to know the hard way to prove that, it's the Gauss-Bonnet theorem. Because we proved the Gauss-Bonnet theorem, you may recall, and this notion of weather characteristic just fell out. It just fell out when our proof of the Gauss-Bonnet theorem. It's in the book we did in class. And then you're like, but wait a second. What if I triangulate it a different way? Well, but this left-hand side doesn't change, right? It's independent of how you triangulate it. So therefore, weather characteristic must be independent of how you triangulate your surface. that obviously seems like we just use a cannon to swat a fly, right? I mean, there must be a simpler reason why Euler characteristic is invariant, and there is. And that is if you take some surface, well, could have a boundary, by the way. So let's say it has a circular boundary. I'll go ahead and put a square. I'll give it a square boundary, right? Or let's say have four vertices on the boundary, and then you can triangulate it however I want here. By the way, you can have triangles and squares, and I'll put a pentagon in here, right? Doesn't matter. And stuff goes around to the other side and so forth, right?
You could have a pentagon.
Sure, why not? I mean, this one has 5 sides, right? As long as it's a bunch of polygons, and it goes around to the other side and so forth. Okay, so these things don't even have to be exactly straight, but. And so notice that what I've done here is this. Okay, let's see here. We've got these sides here, right? But that's actually missing, okay? And then here we have a pentagon, and if we had colored chalk, I could color it and so on, okay? But there's a missing side here, right? So what's the Euler characteristic? Well, what is the Euler characteristic and proving that it's independent is 2 different things, all right? So the proof that Euler characteristic is independent of how you triangulate is really 2 main steps, and I'm going to let you fill the rest of the steps in with your head and convince yourself it's true, right? It's not a topology class. So, but it is, the basic point is the following. If I add a vertex, so, if you can always add a vertex. Right, suppose I add a vertex, like right there I put in a vertex, right in the middle of an edge. If I do that, then the number of vertices goes up by 1 because I added a vertex. But also I split this edge into 2, so one edge became 2 edges, and so the number of edges goes up as well, right? Which means that the Euler characteristic stays the same, right? Because it's minus E plus V, right? So if they both increase by 1, the Euler characteristic is unchanged. The other thing is, what if I add an edge? Okay, so for example, I take. It doesn't have to be this one. I'll go like that. Add an edge, right? Well, I add an edge, so the number of edges goes up. But also notice when I add that edge, I'm splitting this face into 2 faces. It was 1 face, now it's 2 faces. So the number of faces went up by 1 also. And so F goes up by 1, E goes up by 1, so the difference doesn't change at all. And it turns out you can get from any triangulation to any other triangulation by the process of adding and subtracting vertices and adding and subtracting edges. By the way, if adding a vertex doesn't change it, then subtracting a vertex doesn't either, right? As long as you follow some reasonable rules, okay? And so you play with it, and essentially that's the proof.
So these faces, do they need to be planar? Or does it not matter?
What do you mean planar?
Like
The faces.
Yeah.
Yeah, they have to be polygons, yeah. So like just topologically, they're an n-gon. Yeah. Other questions? Yeah.
In the homework, we had to do something like this.
Mm-hmm.
We had to actually show like the Euler characteristic is something. So you had to do like induction, but for like deleting edges.
Mm-hmm.
So I was sort of confused at this, like how to set up the base case. It was like.
So what was the question? I don't remember it.
So we had to like show that the Euler characteristic for a disk and for a cylinder and for whatever was like X.
Okay, just compute Euler characteristic.
Yeah, and we had to like prove it.
Gotcha,
So, like-
gotcha. So all you have to do is triangulate it. So for example, let me take a harder question. What's the Euler characteristic of this mess here, right? Well, actually, it's a disk, isn't it? Right? So if I say, what's the Euler characteristic of this thing, right? Well, it is the Euler characteristic of, in fact, a disk, right? Topologically, the same thing. I don't have to use that triangulation. The choice of triangulation doesn't matter, right? So then this equals the Euler characteristic of this, right? Which number of faces is 1, minus 3 edges plus 3 vertices equals 1. Right? So 1 face, 3 edges, and 3 vertices, 1.
I don't know if in the proof we were allowed to assume that all that a disk is topologically the same as like that triangle. I think is the point.
Yeah, I think you have to show that it doesn't depend on the way that you're triangulating. I think you can't just.
Well, they were telling you to, okay, so I don't remember the problem exactly. You're welcome to read the instructions, but they probably wanted you to triangulate it 2 different ways and get the same answer or something.
They gave us like a proof technique that we were supposed to use,
Mm.
and they like did it for the plane. You can, if you want, you can have.
Show me after class. I'm kind of, okay, so let's just do some more examples. What's the Euler characteristic of, because you're all more concerned with the kind of questions I might ask anyway, right? Because like some of the homework questions are pretty far off from what would be on a final exam. They're really forcing you to think through it, and that sounds like one of those problems. But for example, what's the Euler characteristic of a cylinder? Well, let me tell you how I would do this. You ready? This is how easy this is. You ready? That's a sphere with 2 disks, with 2 faces removed. Am I right? I mean, that's an Euler characteristic of, take a triangle here, and then go like this, right? I mean, that's a triangulation, just as an example, right? And so this thing, but with the top triangle is missing and the bottom triangle is missing, right? So if I want to think of it as a triangulation, I could say, well, how many faces do I have here? I've got the 3 rectangle faces, right? But not the 2 triangles, because remember, there's a gap there, right? This is supposed to be a cylinder without the top and the bottom, right? And so that's 3, and the number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And plus the number of vertices, which is 1, 2, 3, 4, 5, 6. And then I get that equals 0, right? But let me tell you how I would actually do it. I would probably say the Euler characteristic, that this is equal to the Euler characteristic of a sphere minus 2, which equals 2 minus 2, which equals 0, right? So I would probably just say, oh, if I just put in a face there and put in a face there, I would get 2, because I know the Euler characteristic of a sphere is 2. And so, so really, if I just want to know the answer, right? I always just I have this memorized, and I say, okay, just put in some. How many faces do I have to put in to where there's no boundary? Then therefore it has to be on this list because these are all embeddable surfaces in R3. And then I work from there. Just work backwards from there. Yes.
Also, couldn't you just conclude that like that cylinder without the boundaries is like what the piece of paper that you connect for a torus?
Mm-hmm.
So then that has Euler characteristic 0. So.
Pretty close. You gotta be careful about that because if I take this triangulation here, right? If I actually want to stick this together, I have to actually remove these 3 points and those 3 edges. Then I stick it together. You get what I'm saying?
Yes.
If I just sort of put it together, then I've got 2 points where there should be 1 here and 2 points where there should be 1 there, and also with the edges here, I got 2 edges. So effectively, I have to remove 3 points and 3 edges, but 3 edges and 3 vertices cancel. Yeah, but that argument is also valid as long as you realize that 3 minus 3 is 0. Okay, so that's some playing games with Euler characteristic. Ultimately, for surfaces in R3, if they're embeddable in R3, you just need to know this, okay? By the way, let's prove this, because you should never use something you don't know how to prove. We proved the Euler characteristic of a sphere is 2. Now, did we prove the Euler characteristic of a torus is 0? I don't think we actually did we? So we need to do that. Let's just do that real quick. I want to erase, let's see here. Yeah, I think I could erase this, actually. Okay. Okay, so another characteristic of a donut here, right? Probably, I mean, it's just the way I would do it is say it's another characteristic of this, where I identify things like this, right? And then you have to say, well, how many faces are there? Well, technically only 1 face, right? The square, right? How many edges are there? Well, it looks like there's 4, but actually remember, this one is identified with that one's identified with that, right? So actually 2, right? How many vertices are there? Well, it looks like there's 4, but remember, this right here is the same as that one right there, right? Because they're both the end of that edge, right? They're folding over like this, they get identified. But then on the other hand, this thing is the same as this because they're the most beginning of that. So this equals that, and then this is the same as that because they're both the beginning. So actually, this is 1 point, right? And so remember when you let's see here, when you have the donut, right? You have the cylinder identified like this, but then the other cut was like this. So actually, all 4 points come together right there. Okay, in 1 point. Right, you roll off the cylinder and then you stick it together. And so the intermediate step is you have a cylinder, right? So first you see that 2 points come together and 2 points come together, but then you identify those 2 points, and those all 4 points end up coming together, right? And so there's 1 point, right? And so the Euler characteristic of a torus is 0. Okay. It's a little bit of you gotta use your visualization skills, I suppose, right? Be careful about it. Some people love stuff like this, some people hate it. And then, how do you get the Euler characteristic of this? Well, we really need a formula for the connect sum. What is the Euler characteristic of A connect sum B? It turns out it's the Euler characteristic of A plus the Euler characteristic of B minus 2. Okay, when you do a connect sum. Now, why is this formula true? Well, look at what happens when you do a connect sum. If I take a surface and then I want to connect sum it with another surface, right? Remember how we do this, right? The first thing you do is you remove a face here and it leaves you a triangle, right? And you remove a face here and it leaves you a triangle, right? That's your minus 2. Think of this as triangulated. Think of that as triangulated. Remove a face here, remove a face there. There's your minus 2, right? And then you stick it together. Now when I stick it together, these 2 points get duplicated. I mean, there's 3 points and 3 sides that will get duplicated, so I have to remove 3 sides and remove 3 edges. But again, that can't exactly cancels, right? Because edges and vertices have opposite signs, and so you stick it together, and then you have your connect sum. So that's why we get minus 2 for T2 connect sum T2, because why? It's going to be 0 plus 0 minus 2. Right? And then if we want to go take this connect sum that, so every time you connect sum with the T2, you're adding 0 and subtracting 2. Add 0 minus 2, so it goes down by 2 each time. Okay? Does that make sense to everybody? So that's what Euler characteristic is. I think we're reasonably competent with Euler characteristic now. Now, what is a double cover? Let's just talk about that. Let me do it with an example. Gosh. Let's talk about non-orientable surfaces first. Okay. I like to think about non-orientability this way, and that is, it is possible that if aliens were to abduct me after class, and then take me along or back to their home planet and through a black hole and who knows what, something I can't even fully understand what happened, right? And then they return me back to Earth, and when you see me on Monday, I'm the mirror image of myself. Okay? It's probably not possible, by the way, but we can't really for sure prove it. I think some physicists might have some issues with the laws of physics and whether or not they have that kind of symmetry, right? But let's not overthink this, okay? Imagine that for a second, all right? It may not be possible in this universe. I'm not 100% positive. But imagine if I came back and I was the mirror image of myself. Because I went around some, it turns out the universe is not orientable. And there's some path, some orientation reversing path, it's vaguely conceivable. And then you would see me, and what would be the main differences? I would be left-handed all of a sudden. So I think of myself as right-handed, but now all of a sudden you see me as left-handed, right? The part would be on the other side of my hair, right? And whatever imperfections and asymmetries I have would be the opposite. What's weird is I would see all of y'all as flipped, right? I would, because not like I would just see everyone else as on the mirror image. The whole world would seem like it got flipped to me. The door would be on the other side of the room. Everything, right? It would, be very weird for me, right? And but that happens on a Klein bottle. It happens on a Klein bottle actually. And what does that mean? What it means is, let's say we're on this part of the Klein bottle, and you can think of it as like two vector fields, 1 and 2. Okay, and like one, the first direction, the second direction, right? If you take this around a loop and then come back here, what you'll find is, and this is the same phenomenon you have on a Mobius strip. So let's just do it on a Mobius strip. Okay. Which, by the way, is a subset of the Klein bottle. So we can see this quite explicitly on a Mobius strip. See if I can remember how to draw this. Okay. So imagine if I have an orientation here, 1, 2, okay? And then I move it over here, and that's equivalent to this orientation, 1, 2. Now, by the way, there's two orientations in general, right? If I'm in the chalkboard, there's this one. That's the same thing as this. You guys agree? I just rotated it, right? And it's also the same thing as this, right? I just rotated even more, right? But this is in contrast, though, to the other orientation, which is when I switch the two, right? These are all equal, right? I can rotate these guys into each other, and I can rotate these guys into each other, but these are two different equivalence classes of orthonormal unit vectors, right? These can be rotated each other. So you have two orientations. And this is a fact in an n-dimensional space, by the way, because if you say, hey, choose an orthonormal frame, what is an orthonormal frame? If I have an n-dimensional space, it's n vectors, right? So you choose the first, let's call the vectors E1 through En. So first you choose E1, then you choose E2, right? And now we're in three-dimensional space, so I have to choose an E3. Notice there are two choices. I want the one going up or the one going down. You guys see that? So there's always two choices at the very end. And that's why you have exactly two orientations. And if you give me two orientations, right, I can always rotate my by the way, right-hand rule, left-hand rule, right? Two different orientations. I can always, whatever this is, I can rotate this first finger into that first finger. I even can then rotate the second finger into the second finger. But notice my thumbs that are pointing in opposite directions. So given any orientation, I can match up after rotations the first finger, the second finger. In fact, I can do the first n-1 fingers. But at the very end, that nth finger is either happened to line up if I got lucky or it didn't. Does that make sense? The last vector is the one in the orthonormal frame is the one you may or may not be able to line up. All the others you can definitely keep on rotating. When you have 2 dimensions left, you can rotate, right? But when you only have 1 dimension left, you can't rotate in a 1-dimensional space. Either you got lucky or it didn't. So there's always two orientations in any dimensional space. And here you can see that, so the question is there a global orientation? Is it orientable? Well, the answer is, on this case, if you go around here, y'all know what a Mobius strip is, right? You take a strip of piece of paper and then you put a twist in it, right? So we put the twist and I pull this across like this. The 1 is still going this way, but then the 2 is pointing down, right, with the twist. And then when I come back around, I have the 1 pointing this way and the 2 pointing down. And you see that that's not equal to what I started with, right? There's no way for me to rotate this into this, right? So there is no global orientation on a Mobius strip. There is on a cylinder. If it wasn't for the twist, I could define a global orientation. Y'all see that? And so sometimes people will say, well, choose an orientation. Can't do it on a Mobius strip globally. And so now you can say, well, I want to take the double cover is always orientable. It's a way to make things orientable. So this is what I can do. Suppose when I go on my trip, I'm abducted by aliens, and I come back and I've been flipped. And suppose you guys decide to ghost me, and you're like, oh, he got flipped. You know what? We're gonna pretend like he doesn't exist, right? Because we don't talk to people who got their orientations flipped, right? Then now you're like, it's not like I'm not really home. No one even sees this. No, I'm here, right? And so I have to go. I get flipped again, and then I come back, and then you talk to me, right? So the idea is you go around, but if your orientations are flipped, you're not really there. We're going to call it a different point, all right? So in other words, what you do is, if this is your surface M, right? You look at all x contained in M2, right? But you don't think of yourself as a point in x. You think of yourself as an x comma an orientation. That's an O, okay? You're a point. I guess I use P for point. Okay? And then what you do is you look at all sets of points and orientations, and then you mod out by equivalent, equal orientations, right? This equals that, right? Orientations. So each of these would be like, you could think of as an orientation, I guess. And then mod out by equal orientations, and then what you get is a double cover. Okay? So you come back around, and if you think of it as a separate point if you have it. If you don't have your edge is a point, you're a point with an orientation, and you drag that around with you. And if you're not, your neighborhood of points does not include the points around you unless they have the same orientation, right? And so you have to go around again to get back to where you started. So that's the double cover. And so whenever you have a non-orientable manifold, you can always do this double cover to get an orientable manifold. And then you have a global orientation by definition, because you said that I'm defining this global orientation. I just start at a point and I go around. Hey, is this the same orientation as everybody else? Nope. Okay. Well, then you haven't gotten back yet. That's a different point. And you go around, and it turns out there's exactly two orientations. So given a non-orientable manifold, you can always just take this double cover and get an orientable manifold. And it so happens that the double cover of the Klein bottle is in fact a T2. And now why is that? Because remember what a Klein bottle is. A Klein bottle is just a cylinder where you did a weird identification on the boundary here, right? Kind of backwards. Okay, one's going up and one's going down. And so when you go through and you come back, oh, it's not orientable. And so what you have to do is do it again. And so then this gets identified like this, and then this is a Klein bottle. That's a Klein bottle, and now these two things stick together. And when you do that, you get a torus. Okay, so it has to double the volume, and that's how you do a double cover. And so it happens all these surfaces are non-orientable, and they all have double covers, and they're these surfaces. And by the way, since you double it, the number of faces you have a triangulation of this. The number of faces will double when you do. The number of edges will double, the number of vertices will double, so the other characteristics will double. So 1 goes to 2, 0 goes to 0, minus 1 goes to minus 2, and so forth. And that gives you a hint as to what RP2 is, by the way. So now we know what the double cover is. What is RP2? Well, it's half a sphere, obviously. What do you mean half a sphere? Well, you take a sphere, and then erase the southern hemisphere, which I know is very northern hemisphere centric. Right, because you could erase the northern hemisphere just as well. Right? But now you have a manifold with boundary. We're trying to get a manifold that doesn't have boundary, and so the way you do it is you identify antipodal points. Okay, so it's in the same way that a torus, a T2, right, can be thought of as a square. And it's like, if you're playing Asteroids, you guys ever play the classic video game Asteroids from the 1980s when I was a kid? If you go off the top, then the asteroid comes back on the bottom. If you go off this way, it comes back this way, right? Go off this way, it comes back that way, right? Okay, so the point is you go off the top, you come back on the bottom, you go off the left, you come back on the right, and so forth, right? That's identifying things. That's actually a torus, right? Yeah, so asteroids is being played on the surface of a torus.
I like Galaga too.
Does Gallagher do that also?
I don't know. I think so.
Pac-Man does? Oh yeah, Pac-Man does it.
yeah.
Thank you. That's maybe even more mainstream example because that's still very popular. By the way, so with a sphere, you can do the same thing. Just whenever you come off this side, you come back on that side, right? So if you go, your path goes like this, and you come back over like that. And it turns out that's a perfectly well-defined surface. Everything seems normal. It's just this is a representation of it, right? It's not embeddable in R3, so that's why we have to do a representation of it. It is embeddable in R4, by the way. And but a lot of good that does us, doesn't it? Right? I can't draw it, right? I mean, if you can think in R4, then you can visualize RP2. I cannot quite do that. I think there's video. I think you can find videos online where someone will show you what RP2 looks like. So Google that, some cool videos. And then, but then the double cover of that is the sphere. Not surprisingly, we kind of took a sphere and took it, just take, here's the top half, there's the bottom half. Each of those is an RP2. You stick it together, and then you get the sphere, right? And then now here's a very surprising fact: RP2 connects some RP2 is a Klein bottle. That is not obvious, is it? But it's true. And then a Klein bottle connects some on RP2. Anyway, I don't even know how to draw that. Okay, maybe there's probably a way, and then you can just keep on going. The Klein disc, the Klein bottle is almost embeddable in R3, and so I can kind of draw a picture of that. And RP2, I can sort of draw a picture of that. And so there you go. That's what RP2 is, and there you go. Let's connect sums. Turns out these are all surfaces. If you say I want to know all finite surfaces without boundary, so closed surfaces. I don't want them to be infinite like the plane, right? Goes off forever. So if I want it to be a compact surface, closed and no boundary, so I think that's often called a closed surface, compact, no boundary. I'm not so good with vocabulary. Anyway, then that's all of them. That's all of them. Isn't that amazing? We have a complete list. Now you might say, I don't believe you, and that would be a good first thought. Or you might say that seems reasonable. At a minimum, you're saying, how do you prove that, right? And it turns out that's we could do it, and it would take us 3 weeks, something like that. I don't know. I actually took a course when I was undergrad called, I think it was called Geometric. Oh, it has the word geometric in it, like geometric. I don't know. I forget the name of the course, but it's something geometric, something or other. Anyway, we actually did prove it in that course, but we didn't prove the Gauss-Main theorem. So I think it's quite believable. How do you roughly do it? The proof is it turns out, see how we represented a torus like this, right? It's a pretty nice way to represent a surface, isn't it? Turns out you can prove that all surfaces without boundary can be represented as take some polygon, like the stop sign here, like an octagon, and start identifying sides. And then I'll put a solid one here, right? And then a solid one here. And by the way, that is T2 connects some T2, I think. Okay, so that's sort of a stop sign identification, I think. All right, and so what you do is you take, turns out all surfaces, first step one is prove that you can represent all surfaces as a single, with a single face, right? Like first you triangulate it, right? But why couldn't I just sort of start identifying faces, and ultimately just what's the minimum number of faces I could use for a triangulation? The answer is 1. Maybe that's not too surprising, right? But then you're going to have identifications on the edge. Turns out if I take an octagon and just start randomly doing identifying, like this one's identified with that and so forth, turns out there's certain rules that can't be broken. So you have to understand the rules of what identifications you can do, right? Every side has to be identified with another side, but anyway, there's certain rules. So then there's legal ones, and then you just classify all legal ones, and it turns out this is the answer you get. Okay, so anyway, it's actually not that hard. It's quite beautiful. But it would take us like 3 weeks to go through all of it.
So It's interesting that on the left side of the embeddable surfaces, the first example, when you, what is it called, combine with that little hashtag,
Connect some, yep.
When you connect some with the sphere, it doesn't do anything. On the other hand, with RP1, it begins the chain.
Great question. Great question. Because actually, and I think what I can tell was probably on your mind was a natural question. Which is, where's T2 connects S2? Well, you just pointed out that we already discussed that same thing as T2. So adding S2 doesn't do anything. In fact, T2, anything, M2 connects some S2 just gives you M2, right? Doesn't do anything. And then if it's orientable, you can connect some with T2s. If it's not orientable, you connect some with RP2s. But then you're like, wait a second, what if I connect some with T2s and RP2s? I think that was where your train of thought was probably headed. And so, what if I take M2 and then why can't I, or how about just in general, what is T2 connect some RP2? Like, why isn't that on the list somewhere, right? Like, seems reasonable, right? That's because there's another identity, which is this is the same thing as K2 connect some RP2. Which is, it's RP2 connect some RP2 connect some RP2. So this is sort of, in other words, RP2s and T2s destroy each other. Actually, RP2s destroy T2s. That's the right way to understand it. So whenever you have so what we have is these fundamental building blocks are, you think of S2 as like nothing, right? It's like trivial topology. And then you can connect some with T2s and RP2s. But then whenever you have a T2 and RP2 together, the T2s get destroyed and you get 3 RP2s. Okay? Now, why is this true? Well, I can prove it if I assume this classification theorem, because there's 2 kinds of surfaces. Those that are orientable and those that are not orientable. Turns out the orientable ones are all embeddable in R3, and the ones that aren't orientable are not embeddable in R3. So that splits our list, orientable or not orientable. When you connect some with something that's not orientable, that means this whole thing right here is not orientable. So it should be on this list somewhere. And what's the other characteristic of this? Well, that's 0. That's 1. 0 plus 1 minus 2, right, is minus 1. And that means it's this. And you'll see that, in fact, we have a classification, right? Classification is a nice word. Classification. You can classifying things. So the classification of surfaces comes down to 2 things. Euler characteristic and whether or not you can orient it or not. Orientability. So that's the big theorem, I guess, that comes out of this, is that if you want to know precisely what topology your surface is, I need to know 2 things. What's the Euler characteristic, and is it orientable or not? And obviously, once you know that, then just do a table lookup. And there you go. That's it. If your surface has boundary, we'll go ahead and fill in the boundary with a disk, right? So you get one of these surfaces. These are surfaces without boundary, right? Fill in the boundary with a disk, and then and there you go. By the way, here's the closest I can come to an RP2 to tell you what it is. Kind of fun. And that is take a Mobius strip here. Should we let M be for Mobius strip, right? M for Mobius. Okay, I'll spell it out. You take a Mobius strip. Okay, what's the boundary of a Mobius strip? Can we agree it's a circle? There's actually one boundary, right? If you didn't flip it, you'd have 2 circles, the top and the bottom circle, right? But here you've got the top circle and it becomes the bottom circle, right? And then so the boundary there is a circle, right? And so if you take a Mobius strip with a circle boundary and then take a disk, that has a circle boundary. Would you agree?
Yeah.
You guys like zippers? Go ahead and put zipper teeth on both ones, right? Line them up and then zip it up. That's an RP2. Now in 3 dimensions, at some point you're not going to be able to push the zipper anymore. You'll get caught on the zipper. But in 4 dimensions, it will zip up just fine. And you can even draw a picture of that. Remember, RP2 is just the northern hemisphere here, right? This right here is a Mobius strip. If I draw this like this, there's your Mobius strip right there. And this is, the twist is, and this gets flipped when you go over there. Do you guys understand? So this strip in the middle, that's your Mobius strip. And then your disc is the left and right sides. It's actually one disc, right? Because this point gets identified with that, right? And so this shows you how you have a disc over here is identified with the Mobius strip there. Sort of just zip it up along the boundary there. All right. See you guys Monday. The key point is we have a final exam. We only have 2 more classes, right? Next week is the last week of classes, I think. And final exam is 30% of the grade. Make sure you get all the homeworks in. I think that's 30% of the grade as well. Is that 30 or 40? No.
Maybe 40.
Is it, so what,
I'll check.
is it 40 for the homework?
I can look at that.
I think it's
30 for the homework, 40 for the final.
Okay, 40 for the final. Okay, so we don't want to mess up the final. The good news is that I have practice final exams on the webpage. So make sure, I mean, it's like almost the first thing you should do is make sure you work all the practice exams to know what you don't know, right? And then really master, I even have solutions of those practice exams online. So I would master all those tests and make sure you learn how to solve all those problems and be ready for a test like that, right? And you know, that'll give you an idea of where you are. And then, of course, sure, study the homework, make sure you understand all that stuff, right? But homework questions and test questions obviously are quite a bit different. And so I like conceptual things that don't take 3 hours to do, because the final exam I think is 3 hours, but I would rather if you finished it in 2.5 or 2 or something like that, right? There's no reason to have to use all the time. So I'm looking for problems that are 15-minute problems, right? And maybe do like 10 of them or something. So good luck. Start studying it as soon as you can, and then that will relieve your stress and anxiety. And then we'll do some more review and also do more material.